Today let's talk about plotting functions that are created with convolution. And we'll quickly review some of the basic plots, and then at the end we'll kind of have a summary of how to look at the shape so that you can tell what the plot should look like. So first one will be step convoluted with step, and the simplified convolution integral just gives us TUT, and really Laplace, right? 1 over s times 1 over s, take the inverse, it's ramp t. Now, plotting a ramp, I think everybody knows how to do, but let's say we didn't know that, it was complicated, right? So let's try to use the flip and drag method to figure out what the shape should look like. So here we have a step, u of tau, right? And then here's the step that's been flipped in time, minus t tau, right? And then with a parameter of t, we keep advancing it, right? So nothing happens until 0, and then it starts to overlap, and we have a little bit of area, right? And it goes up. And then if we we just have the same delta t, we go up by the same area, right? Now what I'm showing is jags, but as we keep increasing the parameter time, the overlap increases, and this is going backwards in time forever. The non-flip step is going forward in time forever. So it never flattens out. It keeps overlapping more and more and more. And so when you multiply these two functions together and integrate them, convolution integral, right? It keeps going up in time, and it goes up linearly, in time. So now let's do a step convolved with a ramp, right? The best way to do the convolution integral is tau times 1, right? Because we're integrating it from 0 forward. So u of t minus tau, right, is 0 until t minus tau is greater than or equal to 0. So that just becomes 1, right? Integrating that becomes a ramp squared divided by 2. And again, you can do that in Laplace just as well. So here's ramp tau, right? And we're going to flip the step and then drag it this way. And we can see that, as we're kind of increasing our step by the same amount, how far it goes, the area keeps increasing for each step. And not linearly, the change in area is increasing. And that's where we would get RT squared divided by 2, right? But this never comes down, this ramp, and the step, again, it's going backwards in time forever, and we keep increasing it. So there's nothing to ever bring this back down, and so it would just increase. Let's look at another shape that never comes back down, is ramp convolved with ramp, right? Which, again, today isn't how to do that. You can easily look this up on a table, right? And we get t cubed divided by 6 times the step function, right? So here's one ramp. Here's the other ramp that we're flipped and now we're dragging, right? And so, this overlay, right, that area multiplied keeps increasing. And again, these two inputs never go back to 0. So when you're multiplying them, the area just keeps increasing and increasing. In this case, it's t cubed divided by 6. All right. So those are some basic shapes that they just keep increasing, right? And when you're doing a midterm or a homework, you can at least get the idea of what the shape should do, right, before you do all the math. Okay? Now let's just do a step convolved with a rectangle, right? At this point, we use our composite function, right, where we have the simple function is just step convolved with step, which is a ramp, and then we scale and delay as needed. So we get ramp minus ramp, delayed ramp. Now what does that look like? Well, here's our rectangle, which, and then we're going to drag our step across it, right? And first there's no, remember, this is why everything is multiplied by a step function, is that when we're doing this area, it isn't until they start to overlap that there's any area that overlaps that gets integrated, right? So it's 0 before that. And so it basically keeps increasing, and it's just like the regular step convolved with step. It goes up linearly, right? But then what happens is the step goes beyond that, and then you have this area here where it doesn't matter where the edge is, it's beyond time equal to 1, and the overlap never gets any bigger. So that's why you have this linear change up until 1, and then it flattens out. Now let's do a rectangle times a rectangle, right? In this case with the delays, I've programmed it, right? And that's to keep the area of this rectangle equal to 1. Again, step convolved with step, common function will be a ramp, right? And I just keep track of the delays, right? T convolved with, UT convolved with UT, there's no delay there. But then there's a delay of -1 when UT is convolved with -1, right? So those are those two. Then I have minus T minus 1 over A, and then the next one, right? So that there's basically 4 times to deal with. And that goes right into ramps, right? I go up, I flatten, I go down, and flatten, all right? Let area A equal 1. All right, so this is my flip and drag, and I'm going to, I start to go up. Let me try a darker color. All right, I'm increasing, same dt, and the area increases by the same amount, and that's linear, right? But at some point, they overlap perfectly, right? And then it starts to leave, and the area starts to go down to the point where the rectangle is moved past and the area is 0 again. And so it goes up linearly and then changes. And then flattens out, right? Now there's 4 times here, but what happens is when I set A equal to 1, I have T minus 1 minus RT T minus 1. I can collect like terms and go to minus 2 RT minus 1. Now let's set A equal to 2, right? So I'm dragging along, and what's going to happen is I have an overlap, but the amount of time that it takes to overlap is shorter. In this case, it's a half, right? And then it's completely overlapped for some amount of time, right? From here to here. And then that rectangle starts to leave. And then it's completely non-overlapped, and you get that. Now, why is it 1? Well, the area of this is still 1. And so that area multiplied by this maximum of 1 gives you 1. All right. Now, what one could do I don't want to do that one yet, is that what if we had our regular rectangle, but then this was so thin, what if it was only 100th wide and 100 tall, right? I can't show it. That transition time would be 100th. And this would start to look like a delta function. And what would happen is it would be on the scale that I'm drawing it, it would be indistinguishable from the original rectangle. All right. So when we, almost any shape can be a delta function as long as it starts and ends at 0 and the area is 1. But it acts like a delta function when its time is a lot smaller than whatever shape you happen to be looking at. Now, let's do another one, a little maybe more complicated, where we're convolving a step with a delta minus a rectangle. All right, and so this is the delta, this is the minus rectangle. And what we can do is break it up. Well, let's just do the step convolved with the delta function. And notice I've stopped saying that this is ut minus tau, right? I'm flipping a step, right? And I drag it across and I'm integrating. And so the area, I'm sampling at 1. And so what I'm getting is this, is a constant, effectively, right? Now I'm going to do this step with the rectangle, which was what we had done before, is we had done, the reverse step with a positive rectangle, right? And we got this. Excuse me. So now what we're getting, it's just going in the negative direction. And when I add this to this, I get that, which, sometimes you see my drawing isn't that great, but that's the high pass transient response, step response, right? Well, the way I've drawn it, it almost looks like a triangle anyway. So this is the step response of a high pass like function. Now, maybe there's some key takeaways that we can summarize, is that, how should this shape look, right? Should it go up? Should it go down? Should it go up and flatten? Should it go up, flatten, come down, or go up and come down, right? So really, you just look at the flipped shape in time, convolve with this, and you just drag it across. And here I have, I can see as this comes across, the area will always go up, right? Here, I'm going to drag it across, and the area is going to be increasing to the squared, right? Here, this starts and ends at 0. This starts and ends at 0. And so I'm going to go up and come back down, right? Now, when I have a step, reverse step with the impulse response of a low-pass filter, right? I'm going to go up and then flatten, because at some point, I've dragged it, the area, the overlapping area never changes. Here, right, it'll start increasing linearly, but then that overlap area, no matter where I take it, is the same. So up starts at 0, linear transition, and flattens out. Here, though, right, this area is always increasing, and so we're going to drag it across, right? That area will always increase. But then here's the thing. It never doesn't integrate. I mean, it never doesn't overlap. And so it's increasing, right? Here, both shapes go up and come down. And that's linear times a constant integrated is a squared, right? And it does something like that, right? Here it does it even more so, okay, because it's squared. Or this will be cubed type function. And then here we have a rectangle times, something that's effectively starts and ends at 0, right? So the areas, so what will happen, and that's an exponential. So you get some kind of exponential and then some kind of exponential to decay. Now I haven't shown the times, but really this total time, right, if that's 5 and that's 3, the total time it'll be non-zero will be the sum of that, 8. If, this looks like the same, so 2 and 2, the total time it'll be non-zero will be 4. So you just sum these, for shapes, when both of them go up, start and end at 0, you just sum the shape times, and that's how long it is. And so that way, there's, what can happen is, excuse me. All right, this shape here is like that. And then if I convolve it with a UT, it's like that. Okay? And it'll increase, increase, increase. But it'll still keep overlapping. And so this will, it'll have two regimes, right, where it'll go up to the squared, but then it kind of turns into a step, convolve with a step, so it goes up linearly. All right. And then, of course, if you did, you had a rectangle with that shape, right? It would increase linear as it overlaps. Then at some point the area never changes and you get that. All right. So it's super important that you see what's going to happen first, because if you just, what can happen is sometimes you can have like RT squared divided by 2, right? And that just keeps going up, right? But then I can start to cancel this out with a function like this, and it'll go like that. But again, if I keep doing that, it'll go down. Now, when I have these problems, right, that's pretty much a rectangle times, so if I have a rectangle, UT minus U, something like that, and then a kind of a triangle, right? The rectangle does that, triangle does that, right? Starts and ends at 0, starts and ends at 0. I should get something that starts and ends at 0. But many times there's a third function here that will flatten it out. Then a function will make it go down. So it takes another function to even it out, but it'll go like that. So it takes another function to flatten it out, right? Which can be complicated, right? But if you know starts and ends at 0, starts and ends at 0, I'm going to start and end at 0.